All right, so for those of you doing the notes with me, we're going to review just what average rate of change is, but we're going to relate it to the graph of the function. Like in the past, we looked at like the application problem, what was the rate of change between year 1 and 2 when we did the slope. So we're going to do that, but we're going to relate it to the slope of the line on the graph, because a derivative is basically the slope of a tangent line on the graph. So instead of writing y2 minus y1, they're writing it as f of x2 minus f of x1. That's just y2 minus y1 written in a new way. So for number 1, we're just going to sketch this graph first, and then we're going to draw a secant line. So let's sketch, this is a good review, x squared minus 2 transforms down 2 units, and then it's a parabola, so over 1, up 1, over 2, up 4, 1, 2, 3, 4. And I think that's all that's going to fit, right? Because over 3, up 9 is not going to fit. 9. It says, let's draw a secant line between x equals 0 and x equals 2. So here's x equals 0, here's x equals 2. So our secant line is just going to connect those 2 points. That's a secant line. So when you're finding the rate of change between those 2 points, you're really finding the slope of this secant line. And it just says, let's find the rate of change between those 2 points. So if we did y2, this is the point what? 2, 2, and this was the point 0, negative 2. So we're just finding the slope between those 2 points. So if I do y2 minus y1, 2 minus negative 2, and if I do 2 minus 0, I get 4 over 2, right? So the average rate of change, this secant line has a slope of 2, right? Because I went up 2 over 1, up 2 over 1, slope of that line. So now it says, let's do the same thing between 0 and 1 and find the rate of change between those 2 points. So I'm going to draw this secant line in instead. See how that slope just changed? The slope of this secant line was a lot steeper than the slope of this secant line, right? So rate of change is changing on a parabola. Rate of change is constant on a linear function, but not on a curve. So find the rate of change between these 2 points. What's this coordinate? 1, negative 1, right? So I'm finding the average rate of change between these 2 points. I think you can see that it's up 1 over 1, right? It has a slope of 1, but we could do it. y2 minus y1 over x2 minus x1 to just prove that it's 1 over 1, which is 1. So you just practice finding the average rate of change and looking at the secant line, just like we've been doing all year. We just haven't looked at secant lines really before. So I'd like you to do the same thing in number 2. You can draw your secant lines and find the rate of change. Let's make sure we have the coordinates correct for 2 to the x. We would go through 0, 1, remember? And then over 1 up 2, because 2 to the first power is 2, and then 2 squared would be 4. And then 1/2 is dead. So there's my curve for 2 to the x. So you are going to answer kind of B and C and D and E. So draw in your secant line, find the rate of change just like we did in number 1. You all got there? Drawing a secant line, finding average rate of change. Kind of understand what that means now? That should be kind of a review anyway. Okay. So instantaneous rate of change. We've looked at this throughout the year. So we're going to look at this in relation to the graphs on the front page. So it says to find the instantaneous rate of change, we've been using the graphing calculator. So to find the instantaneous rate of change at 1. We're doing this 0.99 value and 1.01 to find the rate of change between those 2 points. So it says, let's use the graph on the front page and draw a tangent line at 1. And then it says, using the graph only, let's estimate the slope of that tangent line and then actually find the instantaneous rate of change. So they want us to find it at 1. So go to 1 on your graph. I'm going to draw it in a different color. How about green? So a tangent line is drawn so that it just touches that 1 point, but it doesn't go through any other part of the graph. So this is definitely an estimate. So I don't know, I'm drawing my green tangent line. So see how it touches that point, but it does not go through the curve? So I did the best I could to estimate. What do I think the slope of that tangent line is? So let's see, if I started at this point, I don't know, it's about a slope of 2 on my graph. Is that about what you got? When you look at your slope of your green line, your tangent line, which just touches this 1 point at x equals 1, I don't know, what would you estimate the slope of that is? It's definitely positive. Mine's definitely steeper than 1. I don't know, about 2 maybe? Is that reasonable? So I'm going to say it's about 2, just from looking at my graph, or maybe 1.5, or maybe 2.5. Now let's actually find the instantaneous rate of change in our calculator. So we want to go to 0.99 in the table and 1.01 in the table and find the corresponding y values. So start at 1 and count by 0.01. So at 0.99, negative 1.02, and negative 0.98. So we're going to actually do y2 minus y1 over x2 minus x1 and see what we get. It actually gives us 2, doesn't it? I think. So the graph didn't lie, right? With our eyes, we could tell it was kind of steep, maybe a slope of 2 or 2.5, but the actual instantaneous rate of change at that point is 2. So instantaneous rate of change is directly related to the tangent line, which is the derivative of the graph at that point. So we're going to talk about derivative next week. All right, I'd like you to do the same thing on that 2 to the x graph. So draw in a tangent line at 0, estimate the slope yourself, and then find the instantaneous rate of change. So see if you can do that process for example 2. So at x equals 0 is this point right here on the graph. So I did that green line slope. Some of you looked at 1, so yours is steeper. So you did that green line slope, but that's what mine did. So I estimated it was, I knew it was less than 1, so I just estimated a half. I didn't know what it was. And then it should be 0.695 is the exact, it's not the exact instantaneous rate of change, but using these coordinates, it's the exact answer from those. So don't round at this step and don't round to the end. So you get as exact as an answer as you can. All right, and this part, it said so far we've calculated average rate of change and related them to the secant line, and we've tried instantaneous rate of change and related them to the tangent line. So we're going to repeat the process for some additional practice and learn how to find the instantaneous rate of change using a limit. So We are going to do this graph now, and we're going to draw a secant line between each of the sets of points and find the rate of change between each of those. And I'm going to show you what h means down here. So where would this function have its vertex? Let's see, I have to do negative b over 2a. So my vertex, we have to review standard form, but my vertex would be at -1 comma something. Once you have the x value, plug it back in to find the y value. So 1 minus 2 minus 6 gives me what, -7? So my vertex for this graph is at -1, -7. 7. Which fits because then my y-intercept is at -6, so that's good. And then this is just the parent function, so over 2 up 4. 1, 2, 3, 4. And over 3 up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you want to draw in all the secant lines, you can. It's going to make your graph look a little bit busy. You know, if you just want to think about your drawing in from x equals 0 to x equals 3, right? Oh, I didn't do 3 on here, did I? Is that going to fit? I'd have to go over 4 and up 16, right? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right, because the first one is going from x equals 0 to x equals 3. It's that secant line, right, between those two pink dots. And if you don't want to draw in all the secant lines, you don't have to, but you are going to find the rate of change between each of those pairs of points. You don't have to do 0 and h, so you can wait on that for a minute. And I wrote the coordinates up there if that helps you find your rate of change. So what this last part means, this is going to lead us into the definition of a derivative. So we're not going to go too far on this today. But if I put a point, if I put a point, we're trying to find between 0 and h. So if I put kind of this imaginary point right here on my curve and call it h comma f of h. So I'm sneaking that in there. So I'm pretending that this point on the graph, this is h. So h is a little bit away from the point in question. I want that h value to get closer and closer and closer until it's right on top of that actual point. So I'm calling this point h, and the corresponding y value is the f of h, right? So when we do like 0.01, this is f of 0.01. If we got even closer, like 0.001, then this would be f of 0.001. So we just studied limits. And so what we would need to do to find this slope is we would take y2, f of h minus y1, right, which was -6, over h minus 0, because our x value was 0, right? So instead of these being coordinates like 3, 9, we're using the coordinate h, f of h. And basically, to find the actual slope of the tangent line, it's the limit of this as h approaches 0. So we want h to actually not be any different. H has to be different to have 2 points to find the slope, but the closer that we can make h, the distance away, 0, the closer to the exact tangent line we'll have. So exploring the definition of the derivative basically allows you to solve this problem, finding the slope of a tangent line at a singular point. So what value of h would allow us to find the instantaneous rate of change when h equals 0, right? That is the instantaneous rate of change, the exact point that we're looking for. So now I want you to find the instantaneous rate of change at 0. So I actually want you to do it using kind of our old method. So if we want it at 0, we're going to go to that negative 0.01 and 0.01. So let's find instantaneous rate of change the old way here. We're going to learn how to find this limit next time using the definition of a derivative. And I think that's where I'm going to stop so that I can do the back page on Tuesday for the people that, you know, are going to get caught up on this. We'll start together on the back, the last problem, right? Because isn't there one more? Yeah. So we'll do that one on Tuesday, but let's find the instantaneous rate of change here. Maybe you can see the pattern that as we got closer, right, our rate of change actually got closer and closer with the secant lines to a instantaneous rate of change of 2. Question? Why is the rate of change not 0? So the only place that it's going to be 0 is actually at the vertex. So the vertex is actually when x is -1. Here is, you're right, there is a rule about the derivative being 0 at any turning point. So to find turning points on graphs, you can actually find where the derivative is 0 and solve for it. But we were looking for that pink one. The vertex wasn't the one that we were looking for, but sometimes you do look for where the vertex is, and that will always be 0, right? Because the rate of change at that point is exactly 0 as it changes direction. So that's where we got to for that.